So hello, welcome back. So in previous video, we have seen the important concepts like phase detector, the concept of phase locking, and voltage control oscillator, popularly abbreviated as VC. In this video, we are going to see the concept of PLL, what is phase lock loop, and we are also going to see the applications of PLL. So what is phase lock loop? So this is the formal definition of PLL. It is a closed loop feedback system. Understand? This is a loop. As you see the word loop in the title. So it is a closed loop feedback system whose output frequency and phase are in lock with the frequency and phase of the input signal. So here we are talking about frequency and phase both. Actually, when we have seen the concept of phase locking, there you must have noticed when phase are exactly locked, the frequencies are also same. So inherently, when we say that there is a phase locking, definitely there is going to be a matching between frequency. So this is how we define the phase lock loop. So it is the feedback system, closed loop system, whose output frequency and phase are in lock with the frequency and phase of the input signal. So they are matched. There are various applications of PLL that you will find in the literature. Few of the applications I have listed here. So one of the applications which is very popular, and that is frequency multiplication and division. Here we actually obtain the output frequency as a multiple of input frequency. For example, from 1 kilohertz, if you have to generate 5 kilohertz, that means 5 times 1 kilohertz. That is possible, and that application is called as multiplication. So frequency multiplication and frequency division is possible with the help of PLL. Next application is frequency synthesizer. Now all of you must have heard the word synthesizer, which is a playing instrument, musical instrument. So there, all of you must have noticed that there are multiple octaves, and every octave, like we say sa, re, ga, ma, pa, dha, ni, sa, every octave has got different frequencies. Every swara, sa, re, all these have different frequencies. So every octave will have 8 frequencies, and then if you have so many octaves, then you will have 7 frequencies: sa, re, ga, ma, pa, dha, ni. So 7 multiplied by, suppose there are 4 octaves. 7 into 4, there will be 28 frequencies that you need to produce. So how do you produce those many frequencies? Do we really use those many oscillators? Absolutely not. So we generate one oscillator, oscillation frequency, basic oscillator, and from that oscillations, using multipliers, we can generate so many frequencies that we want. So extension of frequency multiplier is basically a frequency synthesis or frequency synthesizer. FM detector, and AM detector, FSK demodulator, frequency shift gain demodulator. All these are very important circuits in communication. All this detection techniques are possible with the help of PLL. Other applications are tracking filters, which are used in radars, satellite communication system, speed control of motor, generation of local oscillator frequency in TV and FM tuners. You know that in TV receiver and FM receiver, you require a local oscillator. So we can use PLL as a local oscillator. Tone decoding, telemetry receivers, signal generations, regenerations. So there are plenty of applications that you will find in the literature. Few important applications you can see on these slides. Now it is not possible for us to discuss each and every application. 2-3 applications that we are going to see in detail later. So let us elaborate the concept of phase lock loop. So here you find, here you can see the block diagram of PLL. So as you see, there are 4 blocks in PLL. The first block is phase detector, followed by low pass filter, then error amplifier, output of error amplifier, which is available as a demodulated signal, that is V control, which also goes internally to the internal voltage control oscillator, and VCO output, then again we give it to the phase detector. Don't forget, this is a feedback system, loop system, and that's why output of VCO, it is always given to the phase detector. So let us understand the functionality of this each block. So phase detector and VCO already we have covered in the previous video. Low pass filter you have studied in 4th unit. Amplifier already you know about it. So almost all the blocks are now known to you. So let us elaborate the block diagram and understand the functions of each block. Remember here, so we are giving the input as Fin, and output of VCO, it is fed back to the phase detector. So first block is phase detector. So let us go through this. So what are the main blocks of PLL? Phase detector is the first block. What is the functionality? Detects the phase between input signal and PLL output, which is fed back to the phase detector. So as you see here, we have given this VCO output, that is PLL output, as one of the inputs to the phase detector. And phase detector has job to find out the phase difference between Fin and Fout and generate the proportional voltage V phi. So how it does? We know that the equation, so recall that equation. So V phi is equal to K phi, which is gain of the phase detector or transfer function of the phase detector multiplied by phase difference. One thing you need to remember, that if we use analog phase detector, it always generates two outputs, two components. One is the difference between two frequencies, that is Fin minus Fout, and second is Fin plus Fout. So two signals are generated. One is high frequency component, and this is low frequency component. So Fin minus Fout is a low frequency component. Fin plus Fout is a high frequency component, because there will be addition of frequency, as simple as that. Next block that you find in the PLL is low pass filter. What is the job of low pass filter? It averages the output of phase detector. Very important. So it averages the output of phase detector and gives us the error voltage. So output of low pass filter, we call it as a error voltage. So it blocks high frequency component Fin plus Fout. So if we use the analog type of phase detector, as we have seen, it generates the two components, Fin minus F out and Fin plus F out. Out of that, since this is a low pass filter, it will allow only low frequencies, that is Fin minus F out, and it will block the high frequency component, which we are not interested, because we are only interested in the difference. Now you should remember here that bandwidth of operation of PLL obviously depends upon the low pass filter. Not only that, the order of this filter decides the order of PLL. So if we use the second order low pass filter here, we call the PLL also as second order PLL. So remember here that PLL action is similar to the selective or tracking filtering. So I will elaborate this concept later when we actually see the characteristics of PLL or working of PLL. But if you see the block diagram, you will notice two important blocks here. One is at the heart of PLL there is a filter, and one more very important block is voltage controlled oscillator, that is VCO. So let us continue. So then you have error amplifier. So whatever comes out of the low pass filter as an average voltage or error voltage, that error voltage will be amplified, and it is available as one of the outputs of PLL, which is demodulated output, or we call it as a control voltage. And that control voltage internally it is given to the VCO. So next block is VCO, voltage control oscillator. So as seen earlier, it is basically an oscillator whose output frequency is controlled by changing the input control voltage. And we have seen the equation that F out, which is output of VCO, is equal to free running frequency F0 plus transfer function K VCO multiplied by control voltage of the VCO. So here we know that F0 is called as free running frequency, which is also an important parameter of PLL. So later on when we design a PLL, so that time I will highlight this concept again, that free running frequency we can actually set. Rather, we have to set the free running frequency. So setting free running frequency means you have to choose the components, timing components of this VCO. Okay. So as I have already described in first video on this topic, that VCO has its timing resistor and timing capacitor, which you have to design. So the control voltage which is coming from the error amplifier increases or decreases depending upon its polarity, because V in could be greater than, sorry, F in could be greater than F out. So when F in is greater than F out, the difference F in minus F out will be positive, and in F in is less than F out, then that difference may be negative. So V control may be positive or negative. So based on that positive and negative polarity of V control, the output frequency either will be increased above F0 or below F0. Okay. So basic frequency of oscillations of VCO is always equal to free running frequency, and we are changing the frequency of VCO around this F0. So either it will be more than F0 or less than F0, that depends upon the polarity of control voltage.